Welcome back everyone to week 3's worth of lectures. This is the first lecture, or lecture 3A, and we're going to cover this week in more depth power factor. So as you recall, in the last section we discussed power factor. So now we're going to take a look at power factor in a little more depth. Power factor itself is a relationship or phase of voltage and current in an AC electrical distribution system. If the current and voltage are in phase, the power factor is 1. But very typically they're out of phase. And as we recall last time, this was because of inductive loads. This leads to a power factor of less than 1. Let's take a look at the actual types of power again that make up power factor. In a building, we actually have 3 types of power, or an electrical distribution system, AC. The first type of power, the power that's actually used in a building, this is called real, or actual, or working power, and its units are kW. If it's calculated in a single-phase system, power, or W, is volts times amps times power factor. In a 3-phase system, power, or W, is volts times amps times power factor, similar to single phase, times 1.73. It's important to realize that this type of power, the one that's actually converted to work in a building, can be measured with a meter. On the other hand, the power that's required by the electrical utility company, known as kVA, is what the power company has to provide. Now, if both voltage and current were in phase, kVA would equal kW. But again, because of inductive loads, it's not. So kVA is typically more than kW. In other words, utility company has to generate more power of this type. This power is known as apparent power. Again, units are kVA. And unlike kW, apparent power cannot be measured directly. It's a calculated value. And then finally, as we discussed last time, certain devices or loads within a building, ones that require setting up of a magnetic field, in particular motors, transformers, solenoids, they actually have to have a magnetizing power or reactive power. And again, in theory, that power is returned to the circuit when the phase goes in the opposite direction, when there's a phase change. But in the real world, there's heat losses. So transformers, motors, all those things, part of that power that's given to it to set up the magnetic field is lost. It's not given back to the circuit. And reactive power, or kVAR, can be measured. Now, how are these 3 powers related to each other? First of all, power factor is the ratio, again, of actual power, or working power, to apparent power, or kW divided by kVA. If we take a look at the relationship of all 3 of these powers, they actually form a right triangle and follow the laws of trigonometry and the Pythagorean theorem. What you see here on this slide is the relationship of the 3 powers that we just discussed. Real power on the top, kW, again, which can be measured directly. The reactive power, kVAR, forming a right triangle, also can be measured directly. And then the hypotenuse on the bottom, kVA, apparent power, which has to be calculated. So if we look at this, we can actually solve for the hypotenuse using the Pythagorean theorem, or a squared plus b squared equals c squared. If we look at the numbers from the previous example, we can solve for C, which should give us the apparent power. What you see here on this slide is the math that we go through to come up with the value of the kVA, which in this case was 7,250. Now, once we have that, we can take the real or working power, divide by the kVA, and get the power factor for this particular situation, which in this case is 0.819, which, as you remember before on our discussion, this is borderline acceptable to most utility companies. Once we approach 0.8, the power company is going to start charging an extra penalty for a poor power factor. Now what I'd like to do is take a look at the effects that a poor power factor can have on a building. One thing that ends up happening is I have to have a heavier current flow to deliver the same given number of kilowatts to a load. Now the end effect is I have a distribution system within a building overloaded with excessive current. Now this will add costs to the utility bill also, as we already found out. So given, if I have a power factor of 1, the given kW that I need in my building is 2,000 kilowatts. Now, if I have a power factor of 1 and I have a 3-phase electrical distribution system at 4,160 volts, if we use the power calculation, volts times amps times power factor times 1.73, and solve for the amp draw that I need on this, the amps come out to 278 amps. Now you should remember that to get 2,000 kilowatts of power, that's real or working power, I need 278 amps. Now remember, amp sets the size of the wire. Now that's with a power factor of 1. Let's say our power factor is 0.85. Again, I still need that same 2,000 kilowatts. The power factor is dropped to 0.85. I still have a 3-phase electrical distribution system at 4,160 volts. Again, I solve for power, or I'm going to solve for amp draw. And this time when I solve for amp draw with the new power factor, my amp draw has gone to 327. Now, I'm still needing the same working power. That hasn't changed. But it requires 49 more amps to accomplish that mission. Now, on the other hand, let's take a look at the effect of power factor on the utility company. So, the electrical utility company measures their capacity again in kVA, or apparent power. So kVA equals volts times amps times 1.73 divided by 1,000 to get it into kilo. Low power factor overloads generation and distribution network with excessive kVA. Again, let's take a look at an example. The first example is a power factor of 1. The kVA to be delivered to meet that demand of 2,000 kW at a power factor of 1. So this would be what the power factor or the power company had to deliver to that building in the first example. If I solve for this, the kVA, volts times amps times 1.73 divided by 1,000, if I run the math out, the kVA is 2,000 kVA. So you should know that works out exactly like we'd expect. kVA equals kW. Now let's take a look at if the power factor is 0.85. We still need to deliver 2,000 kW net end result to do the work in the building. This time the power factor is 0.85. If we run that same equation again, the kVA that has to be delivered is 2,353 kVA. Note that it's greater than the kW, meaning more generation for the utility company. And again, generation capacity is the limiting feature in most utility companies. Once they start reaching their maximum generation capacity, they either have to buy generating capacity off the grid, or they have to send some of their customers into either a brownout or blackout situation. Let's take a look at power factor correction. I have a customer that currently has a power factor of 0.72, and with most utility companies, that 0.72 will be in the penalty area of power factor. The same customer at the same time has a monthly demand of 1,208 kW. What's the capacitor correction needed to get a power factor up to 0.92? So what the customer really wants is to add capacitors to his system to correct that 0.72 up to a 0.92. So he basically goes from a penalty phase into a bonus phase. The above is a typical question asked on the CEM exam for the Certified Energy Management exam. So we're going to lay out this calculation into steps. So step 1, we need to calculate the current kVAR. In other words, the current situation, what kind of kVAR do we have to start with? So if we solve for the information that we have, power factor equals kW over kVA, or in this case, kVA equals kW over power factor. We know the kW and we know the power factor. So we can actually solve for kVA, in this case 1677.78. Using the Pythagorean theorem again, we can solve for kVAR, and that's kVA, or C minus A, C squared minus A squared, and you take the whole square root of that to get kVAR. When we solve for that, the current kVAR with the poor power factor is 1163.21. Now that's the current kVAR. Step 2, we need to calculate the future kVAR. In other words, what will the kVAR end up if I have a power factor of 0.92? So again, we follow the same steps as in step 1. We first calculate the kVA because we know the kW, that hasn't changed. The power factor is going to be our new power factor of 0.92. We divide the two out to get kVA. We solve for the new kVAR. So the kVAR now has dropped to 514.49. Again, that's the kVAR when the power factor is corrected to 0.92. Now we can calculate how much kVAR needs to be corrected. We simply subtract the final kVAR that we want to get to from the original. So in this case, we're subtracting 514.49 from 1,163. So we're going to have to correct for 648.72 kVAR. This ends Lecture 3A, or the first of the lectures in Week 3. When you're ready, you can proceed to Lecture 3B. Thank you.